is Mark Himmelstein. I'm the CTO for RISC-V International, and welcome to RISC-V Taipei Day. We're very excited to be here, and I'm going to talk a little bit about the road ahead so you can see where we are and where we're going. So we're going to talk about, again, where we are, where we're going, and we'll hop right into where we are. The first thing I want to say is that we are a open source hardware organization. And that means that we work with all communities. We break down the barriers of countries, we break down the barriers of companies, we break down the barriers of cultures. And when we all get in the room as engineers, all we want to do is a good job. So this is a very exciting, very new thing. We've had open source software for a long time with Linux. This is the first open source hardware chip of this size born in open source. I want to show you a little bit about the ecosystem that we have. So RISC-V is in the middle. We create the ISA, the instruction set architecture. We do the architecture tests and the formal model with the help of various folks, the development partners, folks like IIT Madras and China Academy of Sciences and Rios Labs. And we produce that and keep it in our own repos. But on top of that is the whole software stack that you might expect. And those are worked with the upstream projects that govern them, like Linux or libc or hypervisors and so on and so forth. On the left, you see the tools. Those are required in order to build everything. And on the right, you see the attributes, things like debuggability, security, performance, everything has to have. On the bottom, in this light green, you see the design and the DV. That's machine dependent. We don't do that, but we work with other organizations that are open source and proprietary organizations in order to provide those. So you can get things from Open Hardware Chips Alliance. And then the green things around the outside are things that people sell. And our whole purpose of doing the inside is to enable a viable and vibrant, economic community around RISC-V. So RISC-V has had an incredible amount of growth. We originally saw this slide last year where it said 50 billion cores of RISC-V by 2025. In March, it went up to 80 billion. We believe that's small. There are, very clearly, we know that there are embedded manufacturers shipping 50 million versions of their product with RISC-V on there every month. We know there are embedded things that are doing SoCs with Wi-Fi to enable smart homes and so on and so forth. And we also have things all the way up the spectrum with things like edge computers for networking or compression or other things and caching. And then we have the enterprise and HPC level stuff doing everything that you might expect them to do from retail to science and so on and so forth. So it's just growing. It's a vibrant community, and this is fueled by the open source community. We have been told that by Wilson Research that 23% of ASIC and FPGA projects incorporated RISC-V. It doesn't mean they were the sole processor in there, but as you know, today, with the renaissance in EDA over the last 15 years, it's easier to put a processor in to do a specific function, like security or compression or some kind of ML. And so a lot of people are building RISC-V chips in because it's easy. We provide the flexibility because there is no license fee. Nobody's telling you what you can and can't do. And there's lots of cores out there that you can incorporate in your designs. We have a vibrant growing community with something like, close to 200 corporations that are involved, 1,900 individuals. And as you can see, it's broad and it's almost equally divided between North America, Europe, and Asia Pac. So as you can see on here, we've made incredible progress. There are lots of things on here, lots of great successes that you can see. Everything from individual small designs that are being made available to RISC-V processors built in traditional things like disk drives, to 1,000 cores of RISC-V on a single die to do inference engines. Andes in Taiwan has released a superscalar multi-core with the latest version of Vector, which we're very excited about. So there's a lot of great progress. There are actual products that people are selling, and actual products that people are building into products that are going out to the field. And it's, again, everything from embedded to high performance computing. So this year, we're doing something a little bit different. We are going to go ahead and create this thing called profiles and another thing called platforms. Profiles are just like in other architectures. You might have a set of instructions that work together. They get released on a generational basis. And those are the things we tell the distros about, Linux distros, real-time OS distros. Those are the instructions you should target for your releases. On top of that, we also have a platform definition. So things like discovery, interrupt architecture, et cetera, that are needed to make operating systems basically very portable, obviously with some customization from implementation to implementation. And ultimately, the goal is that you're able to bring an application from one implementation to another implementation and basically get the same results, except for things you might expect like timing. And this is absolutely a very big thing for this year. We're all working towards it, and you're going to see that it's the center of a bunch of our programs. So we have a bunch of programs. The RISC-V profiles is what I just talked about, the platforms you see underneath, but we also have some other programs that are supporting this. And the biggest one is RISC-V compatible. If you pass compatibility tests for profiles and platforms, you get to brand with RISC-V compatible. We also have a RISC-V lab that's doing CI and regression testing, as well as sandboxing. We have development partners, which I mentioned already, which are big institutions, are helping us do the hard work that needs to be done in order to get extensions ratified. And then we have the DevBoard-C program, where we are trying to seed 1,000 boards in early adopters, academia, and distros by June of 2022. How are we doing this? Well, we built a scalable organization. Over the last year and a half, the board of directors enabled a technical steering committee to basically do the day-to-day execution and the strategic planning for all the technical parts of RISC-V. We have two basic committees, the ISA committee for unprivileged instructions and the ISA committee for privileged instructions. There are things that were ratified in 2019, and all the things in white that you see here are being worked on. B is like bit manipulation, V, vector, so on and so forth. And then similar things on the privilege side. And we'll get to some of this stuff in a minute. But I want to point out the things behind the ISA committees. These are the horizontal committees. And we drew it that way because each of the horizontal committees affects everything that occurs in the ISA committees. So if you're doing vector, you better talk to security and make sure you're not opening a hole. If you're doing something in software, you better, or in caches, you better make sure that the software works with it, with the kernels and the hypervisors and so on and so forth. So this is a way to make sure that all the different parts of the ecosystem work together. The ISA is like the shiny big piece, that we see. But the truth is, the bulk of the work is in the ecosystem. And we have to make sure that all the ecosystem pieces work well with the extensions that we're working on. The software organization started this past year with one group. We're now up to 15 groups. It's very exciting. There's lots of stuff going on here. I'm not going to go into it in detail, but suffice it to say, there's two major groups here, the platform group doing operating systems to real-time OSs, and the tool chain and runtimes. Plus, there are some new things that are starting up that are being fostered by the bigger committee, the software committee, around things like ML or Android. Then there are a bunch of other horizontal committees. I'm not going to go through them all, but I'll say the security committee is one of the most important ones. We have a bunch of work going on in cryptography. We have a bunch of work going on trusted execution, and we have some work starting up in things like blockchain. And then the other thing to note is we have this ISA infrastructure committee, which take care of those architecture tests we talked about before, and simulators, and the CI regression testing, and the documentation. So now where are we going? This is the roadmap for RISC-V International. As you can see, there's a long list of things that are getting done in 21, 22. We didn't do much in 2020. And so we had a very big backlog. We had some very big specifications, big extensions that needed to go out, and we've worked to get them out. And you'll see in a second that 4 of the big ones that are listed on here have gotten out. We're going to go through that. But we also have a road ahead. Things like the RV32E, which is 16 registers, bigger addresses, crypto vector. There's a huge amount of things on the roadmap. And then if you look at the top of this, there's a whole bunch of discussions going on, figuring out what we should do next in certain areas. So the way we do this is we start a special interest group. They figure out what the strategy, the gaps, and the prioritizations are. And then they go ask to create task groups that go ahead and do the extensions that are on the bottom. So some of them to point out on the top are things like graphics, communication, and Android. So what happened in 2021? Well, 4 big ones happened. And we're very excited about this. Bit manipulation not only has gone out to public review, it's come back. We're doing the work we need to do in order to get it to ratification. So we have a thing called the definition of done. So this is to do all the compiler work, all the architecture tests, all the simulator work, so on and so forth, and make sure there's a robust ecosystem before we ratify it. Vector is also out for public review now. All the crypto scalar work. So we did a novel thing at RISC-V that's not been done anywhere else. Most people have some vector stuff for crypto, and that vector stuff does things fairly quickly, but it requires a lot of logic. Or you can use just the plain instructions from RISC-V, but that takes like over 1,000 instructions to do one loop of AES 128. So it takes a lot of instructions. So we did something in the middle, something that's an order of magnitude faster than the basic instructions from RISC-V, but doesn't take the logic space of vector. So this can be used for embedded. And we call this crypto scalar. They're scalar instructions, but they have built-in things for things like AES and Chiang Mai. So we're very excited about this. And we believe that this is really going to help the embedded space play in security as they need to. And then finally, Priv 112, there's a whole host of things in here, but the biggest one I want to point out is H. H is the hypervisor. Everybody's been waiting for the support. It's been out there for a while as a spec, but not more in draft form. And now it's gone out for public review, and we expect it to be ratified this year as well. So let's talk a little bit about these extensions. Bit manipulation is broken down to 4 pieces. And you can see we have these names, ZBA, ZBB. Those are sub-extensions, so you can pick and choose. If you want one and not another, you can do that. RISC-V allows you to do that. If you want to get branded with profiles, you have to have them all. But if you're, for example, doing embedded and you only want ZBA, you can do that. That's for address generation. There are some basics around ZBB. ZBC is used in crypto quite a bit. And ZBS is used by compilers and a whole bunch of other tool-like things for single-bit instructions, single-bit values, or single-bit manipulation, sorry. And then vector is very exciting because we have varying length registers, and that's pretty novel in the industry. I'm going to show you some detail, but almost everything you would expect in a vector unit is here. And I'm going to actually skip through this slide and the next one and go to the table to show you sort of a summary of everything. So we have the basic vector stuff. We have a whole bunch of other things that are coming here. We have integer, single precision, floating point. We have fixed point, and we will have quad eventually. Vector also has move ops and other things that you would expect in vector. And the table that I was talking about is here. This table is very, very clear. This table shows you a comparison of where we are. Now, we benefit from our position in history. we can see what everybody else has done before us, and we're very grateful for those. We stand on the shoulders of giants. We think competition is good. We're glad there are multiple architectures out there. But as you can see, for example, we have 100 instructions in our vector, and that's a lot less than other architectures. We do have the variable length registers, and you can go down one thing after another, and we've taken the best of best and put it into our vector story. So we're very excited about that. I think this is going to make a huge difference for machine learning. If you take a look at folks like Esperanto, who are doing big inference engines, they're depending on vector for those things. And I think we will see a lot more things done with vector. We know that the HPC folks in the European Processor Initiative are building vector in. So you should expect to see big things out of this. Cryptography, we talked about this a little bit and why it's novel and what we're doing with Cryptoscaler, but this will give you a better idea about all the pieces that are part of it. So the AES pieces, the Chiang Mai pieces, we also have an entropy source. We also have fixed time behavior effects. People can go ahead and deduce things by the length of time instructions take. Yes, believe it or not. And so these are various things that implementations can use in order to make it very hard to go ahead and do some kind of attack on our chip. The privilege instructions, as I said, there are a lot of privilege instructions in here. The cache management operations you see at the top. So these are standard things like invalidate cache lines, prefetches, block zeros. The basic privilege 112 has 57-bit addressing. That's sort of the next set of things. And then we have a full list of other things on the next slide. And then the hypervisor, this is the page table translations that are pretty typical for hypervisor implementations. We do have cacheable and uncacheable put into memory types. And then we have some miscellaneous instructions that are also very important. But there's a lot of them, and I don't have time to go through them all here. But everything from Java to more virtual memory things to trusted execution, so protected memory regions, and the basis for things like trusted execution. And then finally, the last slide of sort of the laundry list of all the privileged instructions that are here. I think you can see that we've been busy. Again, if you go out to ISA Dev, which is the mailing list, you go to list.risc5.org and see all that stuff. You can take a look at the specs that are out there. There's 11 privilege specs that are out there under review right now, and the teams have done an incredible job. So in addition to these, ZFNX went out, so floating point registers in integer registers, and ZFH, which is half precision, half width floating point registers. So just want to remind everybody, the summit is December 6th through 8th in San Francisco. The call for papers is done. There's a sponsor deadline at the end of October. We realize that travel can be a great issue, so we have both virtual and in person. We're trying to make this as inclusive as possible. If you have any questions, go to this website that's on the screen, and hopefully we'll see you all there either virtually or in person. We are so excited to have RISC-V Taipei Day. Thank you very much to the sponsors and to the folks who asked me to do the talk here. If you want more information about the summit, use the website on the page. And if you have any questions, please ask those questions in the question box, and we'll answer them at the end of the conference. And thank you very much.